As a physicist, sometimes it's really hard to watch sci-fi movies. And you know, my favorite two examples where I had problems in the theater. This is one of them. This is the third. But one time in a Star Trek movie, someone asked, "Are we high enough to reach escape velocity?" And I simply leaned over and said, "No." And then there was an involuntary exclamation from me during a Tom Cruise movie where they're trying to disarm this nuclear bomb, and they've got a plutonium sphere there, and they start reaching for it, and I just involuntarily I say, "No, no, no! Don't touch the plutonium," because you know, anyway. So there are things that I react to in movies differently than most people because of that. And there was this scene in The Martian that at the time, it wasn't the first time I went nuts in that movie, but at the time I was like, oh my God, he's so dead. But then they introduce a whole bunch of fiction and he's not. Okay, so you've got an object in end of a tether, and let's say I'm swinging a yo-yo around on the end of a string or anything on the end of a string. The moment of inertia for mass out at the end of a string that you're swinging around in a circle, that moment of inertia is just mr squared. Straightforward, easy peasy. Okay, so we've got Matt Damon. Here's our spaceship. La da da. All right, and we got Matt Damon way out here at the end of a long tether. And Matt Damon has a mass of, what's his mass? This is about his mass. 80.9 kilos. Okay, Matt Damon, 80.9 kilos. And we've got a tether that's long. This is length, this distance, R, is 1,500 meters. All right, so we got 1,500 meters. We got 80.9 kilos. We know the moment of inertia. Whoop, let me just forget that. I is mr squared. Okay, we know the moment of inertia. And we suppose that Matt Damon has a tiny amount of transverse velocity, 0.1 meters per second. 0.1 meters per second is about, let me get this right, about 1 Mississippi, 2 Mississippi, right? This is about 0.1 meters per second. Okay, so not a lot. And so he's got that transverse velocity V is 0.1 meters per second. That gives him an initial omega naught, right? Omega naught is that velocity over R. Not bad, right? So this is 1,500, that's 0.1. His initial angular velocity, really small, really small. What do we know about angular momentum at this point? Because you watched the slides and you paid attention, right? Angular momentum, L, is omega I. This is equivalent to mv, right, for linear momentum, or I omega. I omega, mv, like linear momentum. So angular momentum is moment of inertia times your angular velocity. So here we are, we've got I, we have omega, and let's put it all together. His angular momentum, when they begin to pull him in, mr squared, v over r, so mr v, right? mr v, and I'm going to put r naught on this, because this is where he starts out, r naught. R naught times his velocity, his very small velocity, we'll do that v naught. Everything has naught, so say that's the beginning. Okay. You reel him in. Angular momentum is conserved. So as you reel him in, what's going to happen as you pull him towards you? Well, angular momentum has to be conserved. Well, now we're at, right, again, omega. Omega is going to be, what's omega? Omega is whatever your new velocity is at your new radius. And what is the moment of inertia? Well, the moment of inertia is now at a new radius. Since angular momentum is conserved, these have to be equal. All right? And so what's this end up being? This ends up being mRV. So we've got mR naught V naught equals mRV when we pull them into some other radius r. Well, the m's cancel out. We don't have to worry about his mass. And so what velocity, right? What the velocity is he going to have when you get him close to the ship? Well, I'm going to solve for v because that's what we're after. That's his transverse velocity at that point. So v is r naught over r times v naught. So you start off with v naught is 0.1 meters per second. R naught is 1500. 1500. And this is 0.1 meters per second. But now we're down at 13 meters, right? That's what R is now, 13 meters. Call it, I'm going to call it 15 to make my math easy. 15 meters. So that's 100. All right? So now, instead of going 0.1 meters per second, he's now going 10 meters per second transverse to the direction you're pulling him. At this point, he has actually, if you look at the spaceship end on, and he's out here, at this point, he's actually begun wrapping around the spaceship several times as you try and pull him in. This is bad, right? This is bad. And so this is one of those things when I looked at, and I you know, conservation of angular momentum, you don't need much at all out there before your transverse velocity as you reel them in starts to become really great. This is exactly the same thing as when I'm spinning and I bring my arms in, I speed up and I put them out and I slow down and I speed up and I slow down. It's exactly the same thing. It's just that I'm on a long tether and so I'm pulling my arms way in, right? All right, that's problem 9.